I'm Rodrigo Cedillo, and today I'm going to present my argumentative exam of modeling of electrical system in engineering. Okay, first of all, sorry if I am looking at other parts, but here I have my notebook and here I have my computer with all the questions and all my argumentative answers. So let's begin. In the first problem, we have a circuit and we have to do the nodal equation, the system of equation in matrix form, the MATLAB solution, a report of the voltage and the electric current, and a simulation in circuit lab. So the first thing I do is the nodal equation and the system of equation. So as we can see here, I use the method of nodal analysis. I defined each node voltage according to the current law, where the sum of the currents at each node equals to 0. Then here I do the system of equations in matrix form. Once we have all our system of equations in matrix form, then we have to go to MATLAB to create our code and put the values. Well, as we said, here we have our system of equation in matrix form, and let's see if it works first. So yeah, it works. So here what we do is that the conductance matrix G was formed using the given resistance, and the vector key was constructed with the input sources. So solving the GK, they give me the node voltage that are these ones. And finally, for this first problem, we just recreate our circuit in Circuit Lab and we see the values that the Circuit Lab gave us. So here is my circuit that I create in MATLAB, and here are all the values that Circuit Lab gave us. And that's all for the first problem. We can go to the second one. Well, in the second one, we have now two circuits. Let me show you. So here we have our A circuit and our B circuit, and we have also to do the nodal equations, the matrix forms. We have to solve the system in MATLAB and to recreate our circuits in Circuit Lab. So here we have our nodal equations. In this problem too, I also apply the nodal analysis again, but this time to a different circuit with fewer nodes. So here we have the nodal equations equal to 0 of circuit A and the matrix form. And here we have the nodal equations equal to 0 of circuit B and the matrix form also. Oh, sorry, for the first problem, I forget to show how I solve for electric current. So I solve it like this. So back to the second problem, I basically calculate the conductance. I create the matrix G and the vector K, and I solve for the voltage. So once we have our nodal equation of the two circuits and our matrix form of the two circuits, we can go to MATLAB to create our code. So this is the code for the circuit B. Let's see if it works. And here are our final voltage. And here we have our code for circuit A. So let's see if it works. And here are our final voltage. So once we have our MATLAB codes already done, we pass to Circuit Lab to recreate our two circuits. So here is the circuit for our B model, and here is our circuit for A model. So with this problem, we can conclude that the nodal analysis stays consistent even if the configuration of the circuit change. So once we have finished our problem 2, we can go to the third problem. Okay, for the third problem, we have this circuit and these three questions. Okay, this is what I did in the third problem. First, I apply the Newton's second law, where the force is equal to this, and I related it to the acceleration by force is equal to mass times acceleration. So there I just substitute the values, and once I calculated acceleration, I use the kinematic equation, that is this one, to find the final velocity, that is this one. Then I calculate the kinetic energy using this formula, and then I substitute the known mass and the compute velocity. Finally, I found the time that it took for the particle to reach that velocity using this formula of velocity, solving for t, and this is the time I get. So this process demonstrates us how applying the law of motion allows us to understand the behavior of particles under fields, the energy, the acceleration, the connecting forces, and the time in a current analysis. Well, let's go now with the fourth problem. Well, in this problem we have to determine the magnitude and direction of the net force at the center of this square, and we have to do MATLAB as well. Okay, so this is what I did in the fourth problem. First, I determined the force vectors at each point using the Columbus law, where the r is the distance between the charge. Then I solve the components of vector f. So since the components of r are negative, we know the direction of the force. Then we do the same with the 3 points here, and then the sum of the vector f on x and y axis. Then we apply the Columbus law, that is this one. However, we are just looking for the magnitude, so we can represent it now as a. Here is the radius, and then I just multiply by the magnitude of force y. With all of that already explained, we go to MATLAB to do our code. So here is the MATLAB code. I have a mistake, but I don't know why. But here are the target points, the magnitude of force, and the direction with unique vector of our MATLAB code. I'm pretty sure I have a mistake in my MATLAB code, and that's why I have different results, but I'm sure that the one that I did is correct. So now we are going to the last problem, to the fifth problem, that is this one. In the part 1 we have to calculate the area. In the part 2 we are doing the charging process. The part 3 we are doing the discharging process. In the part 4 we have to go to MATLAB, and in the part 5 is our critical thinking about this problem. Well, for the fifth problem, for the part A, I use the fundamental capacitance formula for a parallel plate capacitor, that is this one, where the A is the area and the D is the separation distance between the plates. Then I just substitute the given values for D and solve for A. For the part B, I work with the time-dependent charging equation of a capacitor, that is this one. Then I solve for the time required to reach different percentage of maximum charge. I start with the 25%, then 50%, and finally 75%. Finally, in the part C, I solve for the discharging process using this formula. Then I isolate t and I calculate it using the natural logarithm based on the fraction 0.3. With all this done, we move to MATLAB. So here we have the first graph of charge time. Here we have the second graph of voltage across the resistor over time. And here we have the last graph, that is voltage across the capacitor under time. In terms of time constant, I think it's very useful when we analyze RC circuits, because it provides a simple way of predict how quickly the system will respond to the change. And well, that's all. I think it was a difficult exam, but I learned a lot, and thank you to my professors.